Today I'm going to skip the third page of the notes. It was the page that we were on in class. I'm skipping it because basically it just developed how scientists went from delta S of the surroundings to realizing that these reactions could be spontaneous if they were run at the correct temperature. So we don't need to discuss that. We know that, as I mentioned in class, water will melt. It's not going to melt at -5 degrees, but it'll melt at +5 degrees. So right there is a great example of how a reaction can be thermodynamically favorable once you supply the proper temperature conditions. So what we're going to talk about today, the focus today is on the last part of our thermodynamics, Gibbs free energy. This is a huge concept. Basically what it says is that if you want a reaction to be guaranteed thermodynamically favorable, the reaction has to release free energy. The symbol for Gibbs free energy actually makes sense. It's a G. If I express it as a change in the Gibbs free energy, then it would be expressed as the delta G. When delta G is negative, this type of reaction is called exergonic, meaning it releases free energy. So this is going to release free energy. In other words, it's going to do work. It can do work for us. Just like your phone, as we mentioned in class again, when your phone's operating, your phone's turned on, it's doing work for you. If the delta G for a reaction is positive, oh, by the way, an exergonic reaction is also thermodynamically favorable, so we'll put TF next to that. If the delta G for a reaction is positive, we say that it's endergonic. This is not spontaneous, meaning you would have to import a constant source of external energy. Talked about in class how plugging your phone in for the night, trying to recharge the battery, requires constant input. You don't unplug it and then it keeps charging. You have to keep it plugged in to keep it charging. That would be an example of an endergonic reaction. It would have a positive delta G value and it would be non-thermodynamically favorable. The benefit of using Gibbs free energy is that it calculates for the system. And remember, that's really what AP is going to focus on is what is the delta H of the system? What is the delta S of the system? What is the delta G of the system? It shows us how temperature influences the spontaneity of a reaction. So that's another reason it's important. There are several ways to calculate Gibbs free energy. Method number one is probably the most popular equation for calculating Gibbs free energy. Take a look at it. It says that the Gibbs free energy of a system, the amount of energy that can be released or absorbed to do work, is equal to the delta H. We know how to calculate enthalpy. It's equal to the delta H of the system minus T delta S. So here we've got the delta H minus the temperature times the change in entropy. This makes sense when you guys think about it. This makes sense because the units on delta S are usually in units of joules per unit of Kelvin. Every time I make 1 degree increase of Kelvin, I'm going to get more chaos, more craziness in my system. The gas particles, the solid particles, the liquid particles are going to move faster. So look at what happens if I multiply temperature in units of Kelvin. Big indication here, you've got to have Kelvin units here, guys. The Kelvin is going to cancel the Kelvin unit. And you're just going to be left with an energy unit. This should make sense to you because delta H is an energy unit, and you have to add and subtract units that are identical to each other. So I'm going to have an H in kilojoules, oftentimes S in joules. One student already texted me today and asked, Mrs. Minton, if delta H is in kilojoules and S is in joules, does it matter which one I convert to the other? And it shouldn't matter. Just know that if you convert your kilojoules to joules, then your answer is going to be in joules. And likewise, if you convert the joule in the entropy unit to kilojoules, then you'll be taking a kilojoule minus a kilojoule, and your delta G will be in kilojoules. Method number 2 is the method that we've already seen using Appendix 4 for both enthalpy and entropy, products minus reactants. Method number 3 we've seen as well. It's delta H calculation with a Hess's law application to get delta G. We're going to focus on method 1, a method that is focused on quite a bit in the AP chemistry test. Take a look at how it takes the equation delta G is equal to delta H minus T delta S, and it's going to give us all the possible case scenarios. In other words, what happens if my enthalpy is positive? Now remember, that means that the system requires energy, and we really don't want to deal with those types of systems. But if you look, if delta H is positive, that's not good. So sometimes I tell students to put to put a sad face there, like, oh no, I gotta add energy to the system. At the same time, imagine that same system that requires an input of heat is gonna get more chaotic. That's what the universe wants. So we'll put a good face by that. As expected, this reaction could be spontaneous. We call it a determinant reaction. It's spontaneous under determined conditions. This should make sense. Look at the equation. See how it's T multiplied by delta S? Whatever that temperature is, it's going to make delta S's effect seem larger. So look at what it says. You've got a good delta S. Run that reaction at high temperatures because it's going to ensure that the high temperature is going to multiply that good entropy, and it's going to ensure that your system can be spontaneous. If you have a positive delta H and a negative delta S, so positive delta H's are not good. That means that your system's having to absorb energy to do things. Negative delta S, you're decreasing the entropy. That's the opposite of what the universe desires. As you would have guessed, this is always going to be spontaneous, no matter what the temperature is. Let's take a look at another scenario. What if you have a negative delta H? This is good. It's going to release enthalpy. Ooh, but it's going to go down in entropy and get less chaotic. That's the opposite of what the universe calls for. This could still be spontaneous, but you're going to want to run it at low temperatures so that you're not multiplying the entropy by a large value. You would also need that exothermic value to be large so that it can guarantee that the enthalpy will help the reaction to be spontaneous. Basically, what we're looking at here is the system can be spontaneous, but you need either good enthalpy or good entropy. So let's look at the best case scenario. A system is exothermic and it increases in entropy. Yay, everything's good. It's what the universe desires. This reaction should be spontaneous at all temperatures. I'm going to stop this video and I'm going to do the calculation examples in a new video. See you later.